a matrix A times a vector B, then the way everybody computes it is you take dot products, inner products. You're looking up here. Should I maybe just point up here, but you see them. Row 1 dot B gives you the first component, and row M dot B gives you the last component. So that's how everybody, including me, multiplies a matrix by a vector. But it's not how you should understand it. Right? So I'm separating the computation from 2 to AN, so the matrix has n columns. And, oh, I'm sorry to see an A2 there. Oh, horrible. We mean to have a B1 to Bn. Here's the Bn. So that's the matrix with those columns. So I'm using the columns of the matrix. The wonderful thing about linear algebra, and all the sort of nice algebra, is in the relation between the columns of a matrix and the rows. They're two different things, different numbers, in fact. If the matrix is not square, you may have m rows and n columns. And it's the neat connections between those m rows and the n columns that's where the mathematics begins. Okay, so the same answer comes from the columns times those numbers. In other words, suppose I have a column A1 and a column A2. Two vectors. I hope that's okay for the system. And now I want to add those two vectors. And I want to do it by a matrix multiplication. So it's simple. To add those two matrices, those two vectors, I just use a 1 and a 1. And the sum is A1 times 1 plus A2 times 1. So adding vectors, or taking combinations of vectors, is exactly this type of multiplication. And, of course, a key part of understanding linear algebra is, suppose I have two vectors or more, and I take, well, I can add them, but suppose I take all combinations. So suppose I take all constants C and D. So C times A1 and D times A2. Can you visualize what you get from taking all C and all D instead of just 1 and 1, allow any two numbers, C and D, then this is a whole lot of vectors, a whole lot of results, outputs, and that you really have to, it's good to see linear algebra also in geometry. So the geometry is that all of these, all combinations of A1 and A2 will fill a plane. Well, almost always a plane. Of course, every mathematician has to say, maybe you don't get a plane. Maybe you only get a line. Because if A1 and A2 were in the same direction, then their combinations are all in the same direction and you only get the line in that direction. But mostly it's a plane, right? Anyway, you see all this. Okay. So that's like my first day, which my first lecture is always to begin to let students do multiplication in this using columns. Okay. So now this is, yeah, so those are inner products. I call those inner products level 1, level of numbers. Now I say low level. Don't do it. Okay. Next combination is level of vectors. Here we have level of vectors, combination of vectors. Okay, we're moving up in life. And now I want to multiply matrices. And this is what I don't, this is now not in the open courseware, but it will be in the next time I teach linear algebra, for sure. So now I have matrices, A and B. Instead of a matrix and a vector, I have two matrices. Okay, everybody knows how to multiply matrices. But it's not on this slide. That's what, maybe I put it on another slide, or maybe I thought, okay. No, I don't think I did. Everybody knows. To multiply a matrix by a vector, you do, well, can I just draw it here? A matrix A times a matrix B. So you get a matrix AB. And if I multiply row 1 times column n, let's say, then that dot product is that number, right? We all know that. But that's not the way to understand. That's low level. That just tells you one number in the answer, and you have to get all of the numbers and understand the big picture. And the big picture is different. The big picture is not rows of A, not columns of B, but columns of A, those are columns, times rows of B. And now you get AB. And what do you get from this way to look at it? I just think this is the right way to think about it. And of course, this is not special relativity. I mean, this is like known. Everything here, of course, is known, but it's the emphasis that's different. So what am I doing here? So I multiply column 1, call that A1, column 1, that's a column vector, times this row, first column times first row, B1 transpose. Let me call that first row B1 transpose. So that gives me a small part of the answer. But it's a different part from that one number, because A1, B1 transpose is a matrix. It's not a number. When I multiply a column by a row, let's do an example. A column 1, 2 times a row 3, 4. So it's a matrix. You see I left space for a matrix. It's 3, 4, 6, 8. And that's that's the whole answer if I had just one column times one row. But if I have n columns times n rows, this answer is, well, that's what's on the screen at the top. So I still like chalk. I hope this is okay. It's a little old-fashioned, but here I've written it. So that A1, B1 transpose, that's my first matrix, and then the next matrix, and the last matrix. So I'm adding up these. I'm adding like matrices like that. So this might be 1, 2, and then this one might be 5, 6, and this could be 3, 4, and this could be 7, 11, something. We would have a 5, 6 times a 7, 11. That would be another term. But you see the point. That you see it, right? That you're adding up these matrix pieces. That's level 3 matrices. In numerical linear algebra, we always distinguish between level 1, level 2, and level 3. And here we're doing it for pure algebra. Okay. So here was an example. Right. Okay. Now why do I insist that this is a good thing to know? Okay, so that's maybe my talk for today, and it actually will be the beginning of my course in 3 weeks at MIT. Okay, let's understand this matrix. Column times a row. That's a column times a row, and that's a typical matrix. So what, if you look at that as a matrix, what kind of a matrix do you see? I guess I immediately see that I have to use the idea of rank. So what is the rank of a matrix? It's the number of independent columns. So this has 2 columns, 3, 6, and 4, 8. But are those numbers 3, 6, and 4, 8? If I draw them, 3, 6 is up here, 3, 6. 4, 8 is up here. They're in the same direction. So this is rank 1. That's a matrix of rank 1. And let's see it again here. So 2, 4, 6, 12. That's a matrix of rank 1. You could, I don't know if you like to take determinants of little tiny matrices like that. The determinant is 24 minus 24, it's 0. The matrix is not invertible, it only has 1 independent column. And similarly here, the determinant is again 0. But then when you put the 2 together, you have a rank 2 matrix, and it's the correct answer. And you can easily check that the answer is that you did the right operations. You did the same operations that you always do, but in a different order. Yeah, maybe the slide will show that. Okay. So that's my starting point. That's very fundamental, but we'll move onward. Okay, so level 1, level 3. So I just want, this slide is just to mention that the 2 ways of multiplying matrices take the same number of steps because they do the very same multiplications. If I do row times column, that's the inner product, the old level 1 way. So row times a column is n multiplication. And then I have n squared numbers. Yeah, let me say it over here. So the level of the old way, row times a column is n multiplications, and then I have n squared of those, so altogether n cubed for AB. In the other way, this way, a column times a row took, that's n times n, that's n squared multiplications, but then I just add up n of those, so n squared times n of them is the same n cubed, the same operation. Okay. So, well, this is just one transparency, but I just like to emphasize the most important law. The reason we multiply matrices the way we do is that fact is true, that if I have 3 matrices, A, B, C, I can multiply AB first, or I can multiply BC first, and then I get the same answer both ways. Yeah. And there's a nice proof with columns times rows. That law is, I find that if I'm giving proofs in my linear algebra class, that almost all the proofs end up fundamentally using that law. Okay. And here's some examples of multiplication. Because I will, multiplying a matrix by its transpose is an important computation in linear algebra. And of course it comes up with symmetric matrices. Yeah, we'll say more about symmetric matrices. Okay, and here's a direction of applications which I'd like to include in the course. Because so that's a graph at the top. That triangle would be a graph with 3 nodes and with 3 edges, so very, very, very small graph. But the graph of the World Wide Web would be much bigger. The nodes would be all the URL, you created a node, and the edges would be links to other nodes, and it's a giant graph. Or our brain is a fantastic graph, which we don't understand yet really at all. I mean, that's the big problem for the 21st century, is to understand the graph of the human brain. So, anyway, the point is that the graph converts to a matrix. Applications of mathematics come as matrices, very, very often. And so whatever we learn about linear algebra, we use in good applications. Okay. All right, this is really the central slide of the talk now, of what I want to do. So what I thought I would do today is to organize the subject of linear algebra with those 5 steps, and connect those 5 steps to matrix multiplication. And I will, so the first step up there, so this, if you can like focus on one transparency, one slide to sort of see the content of the lecture, the organization of today's lecture, and also of my lecture on Thursday at Hongo campus. Let me just explain. These are you could say 5 great theorems of applied linear algebra. 5 great problems of applied linear algebra. Problems are the lifeblood of mathematics. Good problems. Okay, so on the left is a list of factorizations. Here's the list of problems. AX equal B, solving linear system. So I'm looking now at the first line. Solving a system of equations AX equal B. Let's say n by n, square matrix. Then how do you do it? Well, you could do it by determinants, but not if you want to finish in a lifetime. So elimination, subtract multiples of one row from another row and simplify the matrix, and then you can see the answer. So AX equal B, when you do that elimination, and I'll show, so this is what the talk will do here. Elimination, when you describe that elimination step of subtracting multiples of one row from another row, which my textbook, of course, and every textbook would do. In the end, it turns out to be, what you've done is you've started with a matrix A, a square matrix A, and you've ended with a triangular matrix, U. And the mathematics is the connection of the A you started with and the U that you reached. And the connection is up there in the corner. There's a lower triangular matrix that connects those two. Maybe you've seen the basic, this goes back thousands of years. Well, I don't think A equal LU goes back thousands of years. The idea is old, but so that's my point, that I would like to see ordinary elimination, the most famous, most used algorithm in linear algebra as a factorization. So when I say a factorization, I mean you start with A and you break it into factors. So when we were doing matrix multiplication, we started with L and U and got A. But now I'm starting with A and I want to show that it breaks into factors L times U. And if I can use, do you use MATLAB? I'm the MathWorks professor at MIT, but I'm not any good at coding MATLAB. I'd never write a MATLAB code that works. I hope that's not on video because I shouldn't admit it, but it's true. Never works. And it's my fault. Okay, but the code, here I don't have to write a code, it's already there. It's just LU. So that's the most used algorithm. Then the next one is called Gram-Schmidt. I'm not sure if you use those words. The guys who had the obvious way to end up with, you have some columns in A, but they're not orthogonal, and you want to get columns in Q that are orthogonal. So that's line 2 is making vectors orthogonal. And that's the application. And that's QR is the, you see how the MATLAB command is named after the factors, QR. Okay. That would be in my lecture and in the notes for the lecture, but maybe I'll go not spend a long time on QR. Then the third one there is a big, big theorem, and beautiful theorem in mathematics, that if I have a symmetric matrix, so S stands for symmetric, then its eigenvectors are orthogonal. That is a great, great fact of linear algebra, that the eigenvectors of a symmetric matrix are orthogonal, or can be chosen orthogonal. And the eigenvalues go in a diagonal matrix lambda. So here's SQ equal lambda Q. That says Q is an eigenvector, lambda is the eigenvalue, and of course the command to produce Q and lambda is I, EIG, or eigen. And then if the matrix is not symmetric, let me stop a moment at the spectral theorem, because that's so beautiful, so beautiful. And I mean, really, I think of symmetric matrices and orthogonal matrices as the royal family of linear algebra. Those are the best. Symmetric matrices S, orthogonal matrices Q. Symmetry, everybody knows what that means. Orthogonal matrix means that Q transpose is Q inverse. Q transpose times Q is the identity matrix. The columns are unit vectors orthogonal. So maybe I should say imperial family. They're the imperial family of linear algebra. And then number 4 is lesser family. Because if the matrix is not symmetric, then maybe the eigenvectors are not orthogonal. So, but I will still find it. And then number 5 is a factorization that close to Professor Iwasawa's. And it's very important today. So, and it's not in every linear algebra course. And it says that every matrix A, every matrix, rectangular, square, can be factored. Let me just be sure. So that U and that V are orthogonal matrices. I didn't call them Q because because there are 2 of them. That's the point. with a singular value, the SVD, the singular value decomposition. Here we have SVD. That they're singular vectors. I don't call them eigenvectors now, I call them singular vectors. And there are right singular vectors like V, they're orthogonal. And there are left singular vectors, U. They're also orthogonal, but the V's and the U's are different because they're not eigenvectors and the matrix is not symmetric. Now, if the matrix is symmetric, we can connect everything. But if it's not symmetric, that's just a beautiful, number 5 is a beautiful fact. Here I've written it out in words. You see that all this, all 5 use the same important families of matrices. Triangular, those are sort of easy to find, easy to work with, but not beautiful. Diagonal, those are infinitely easy to work with. And orthogonal matrices, Q from the eigenvalues of symmetric matrices, U and V from any matrix. But I needed U and V, I couldn't just have one. Those are orthogonal matrices. So again, orthogonal means the inverse is the transpose. I go slowly on this slide because now I'll speak about a little more detail. And actually the last one will be more the subject of my my new course this spring, actually, and my lecture on Thursday at Pongo, the singular values and the applications of that. And the command there is SVD. Right. So I took time so that you would see that those are the 5 great factorizations of linear algebra, of applied linear algebra. If you want to use the matrix, then they don't, the number 5 allows any matrix A. Number 3 allows any symmetric matrix S. The others have possible failures. And then you bring in the Jordan form for eigenvalues, and you bring in echelon forms for elimination. But those are the beautiful ones. Okay. So, can I just see where we go? Okay, this is the symmetric one. Yeah, so symmetric, this is the beautiful thing. That eigenvectors and eigenvalues of a symmetric matrix. Yeah, I just want to show you where the factorization comes from. So I have eigenvectors. So now if I put those eigenvectors in the columns of Q and multiply, I get lambda Q, because they're eigenvectors. And so I now have SQ equal Q lambda. That's what that, if you take that matrix with lambda Q's and split it, it splits into Q times lambda in that order. And then you have the spectral. That's the famous spectral theorem. And this is the property of Q, the orthogonal matrix. Yeah. Yeah. I don't think I need to say more about the spectral theorem. That's in every linear algebra. In fact, it would be a suitable finish for most linear algebra courses, but now I think you should get to the SVD. You should get to the SVD. I think the SVD is the thing to get to. I don't get to the Jordan form, which tells you about eigenvectors when there are not enough eigenvectors. That's sort of the disaster of linear algebra, not enough eigenvectors. But there are always the singular vectors, the U sigma V transpose is always the same. Okay. Okay, here's elimination. Oh yeah, so what's the point of this slide? Forgive me for doing a 2x2 elimination system. This is like back to school here. But I just want to see how it gives me LU. It gives me L times U. Okay. So there's my matrix, 2, 3, 4, 11. You see the two coefficients, 2, 3, 4, 11 in the problem. And you see the elimination. So what was the elimination step? What was the elimination step on the top row? I subtracted 2 times row equation 1 from equation 2. And I got a 0x. That eliminated x. That's why it's called elimination. So now if I just look at the numbers, 2, 3, 4, 11 changed to 2, 3, 0, 5. Okay, I just want to think what happened there. What happened to that 2x2 matrix, 2, 3, 4, 11? I think 2, 3, 4, 11, so it started with 2, 3, and it took twice that row, 4, 6, and it removed that matrix, that piece, that 2, 3, 4, 6, it took it out of the matrix A. And what did it leave? So it took the 2, 3 away, so of course it left 0, 0. And when it took the 4, 6 away, of course it got that 0 there. That was the whole idea. And we were left with a 5. So, and that's what elimination always does. Can I say that in algebra words? The first step of elimination on the columns of the matrix A, remove from A rank 1 matrix. A column times a row. A column times a row has been removed. It's that 2, 3, 4, 6 is the column times a row. In fact, it's that column times that row. And it's left a smaller matrix. And now that by induction, you continue, and that smaller matrix is itself is a rank 1 matrix, just 0, 1 times 0, 5. So are we okay that matrix started out, and here's the first step of elimination to take this away, and the second step of elimination to solve that part. But now we have a sum, that plus sign, a sum of a rank 1 matrix and another rank 1 matrix. So I just put the 2, 3 in the row and the 0, 5 in the row, and I put the 1, 2 in the column and the 0, 1 in the column. And I have a matrix multiplication L times U. You may say, you will say, trivial. But still, I think it's right. It's the right way to see the steps of elimination. Remove a rank 1 matrix at every step. So after n steps, you've got n rank 1 matrices. Then but the sum of n rank 1 matrices is AB, is LU here. Are you okay? I won't say anything except that for years, I'll say, for years I would find LU by thinking of rows times columns. And it was always unpleasant. It was always tricky. But I think this is just the right way. So that's one way to see that Gaussian elimination, ordinary elimination, produces L times U. And I think that's a fundamental fact in linear algebra for the most important, the most used algorithm in the subject. Okay. So that's like LU. Oh, I had to get my strength up to do a bigger one. 3 by 3. Believe me, there's no 4 by 4. 3 by 3. So do you see that you see what's happened there? The top line is the key. The first step of elimination peeled off a rank 1, column times row, and left a 2 by 2. And then the second step peeled off a column times row and left a 1 by 1. And then when I put them together, I had LU. Yeah. Okay. So that's the LU, the famous LU algorithm with proof, actually, with proof. Okay. Gram-Schmidt, not going there, all right, to help with Gram-Schmidt. I mean, we could do it. It would, we can think of each step of Gram-Schmidt, each step of, so Gram-Schmidt, what's the point of Gram-Schmidt? Is you start with independent vectors and you choose perpendicular vectors. But, yeah, so it's the place where orthogonal vectors come in. But it's straightforward. Yeah, independent vectors find orthogonal. So I see that there's a handout with the new paper that does these, so I think I can take this here. How about eigenvectors? Okay. You've met eigenvectors, I think, AX equal n to x. And the beauty of eigenvectors, what is it that's great about eigenvectors? If you add A and B, you don't know the eigenvectors. It's not nice. But if you multiply A times A, or if you invert A, or if you solve a differential equation with the matrix A, the eigenvectors stay the same and make the problem simple. They make the problem 1 by 1. Yeah. So the eigenvectors of A are the same as the eigenvectors of A squared, the same as the eigenvectors of A cubed, and then, of course, you don't always have eigenvectors because only certain special vectors are eigenvectors, but you can combine them. So that's the theory of eigenvectors, the application of eigenvectors. This is so eigenvectors give a deeper look inside the matrix. So I think of LU and QR as a different and more elementary factorization from eigenvectors and singular vectors. Those you really go deeply into the matrix. And of course, the computation becomes more tricky, but we have good algorithms. Okay. So, I couldn't resist creating an application of movement of people. Well, this is an extreme application. Right. So these are, so suppose each 10 years, this is an application of eigenvectors. Oh, forgive me, it's stupid. But anyway, it's you see it. So it's important because it brings the idea of steady states in. It shows one place where eigenvectors, if you have an eigenvalue of 1, then that means a steady state because when you multiply by the matrix, you don't change. The eigenvalue is 1, AX equals X. So here's my small, very small example. So brings in probability. Okay, so suppose that every 10 years, the result of people moving between Tokyo and Kyoto is that everybody in Tokyo stays in Kyoto, in Tokyo. I don't know if that's likely. But, and then Kyoto people, if I was in Kyoto today, I would have changed it. But here, I made Tokyo more attractive. And Kyoto people have stayed in Kyoto and have moved here to Tokyo. So after one period of time, you see that the population started out T and K, populations of Tokyo and Kyoto. After one period of time, half of K is now in Tokyo. After another period of time, 3/4 of the original K is in Tokyo. And after n periods of time, there's only 1/2 to the nth of the population of Kyoto is still there. And of course, the steady state is everybody lives in Tokyo. I hope that this lecture is not being shown in Kyoto, but I hope that they produce. Anyway, this is a class of matrix problems that with this very small example where eigenvalues and eigenvectors tell you everything. Okay. That matrix there and this matrix, this second example is called a Markov matrix. These are Markov chains. So, yeah. And computing eigenvalues. Let me say just a word about computing eigenvalues. So of course, we just call the command QR. Not QR. We call command I. I give a matrix. Gives the list of the eigenvalues. But that's not a simple problem. That's one of the great achievements of numerical linear algebra is to find a good algorithm to compute eigenvalues. And it's easier for symmetric matrices, but so it's a challenge. I won't maybe talk about the details of computing. So you see, in a way, there are three parts to linear algebra. There's the abstract linear algebra, which I learned from Professor Iwasaki. There's the using linear algebra, which that's my theme today. And then there's a third thing, the computing in linear algebra, which is another specialty. And we have good codes for many of those problems. Yeah. Okay. So these are eigenvalue discussions. Yeah. Okay. I think maybe this is a point, if it's okay. I'd be happy to answer any questions. I was thinking to show you, if I may, parts of the open courseware, but do you know, how many have watched some, not mine, but some of MIT open courseware? Have you? Oh, wow, a lot. Okay. I get messages from people who watch the linear algebra on open courseware. Some of the messages say, this is what I watch as I go to sleep. No, I'm not sure if I should think that's a very big compliment. That it says them, gives them a comfortable sleep. But that's an important thing. So, and it's very nice experience and completely unexpected experience that the linear algebra lectures are watched quite a lot, and I get a lot of very, very nice messages. So, can we start maybe with just, they were made 15 years ago, and let me tell you my reason to make them. I wanted, the math department at MIT had some fabulous lectures. I'll write the names of one. I write Rota. So, G.C. Rota. So he was a terrific lecturer, just great. And he was active until the time when video started, but then he passed away. And I thought, so sad that nobody ever could see him lecture again. So anyway, I thought I would try by an example to get other people like Rota to do their lectures on video so they could be seen again. Anyway, let's just start with lecture 1, but only for a short time. Thank you. And then, shall I pause at some point? Well, I'll stop this one and be ready for
Hi, this is the first lecture in MIT's course 1806, Linear Algebra, and I'm Gilbert Strang. The text for the course is this book, Introduction to Linear Algebra, and the course webpage, which has got a lot of exercises from the past, MATLAB codes,